Chapter 12, Deflection of Beams and Shafts, Part B, Moment Area Theorem, example number 3. So in this example, let's see what we have. So if we have a two simple support beam at A and B, as you can see here, handling a concentrated load of P at its center. So solution one is just by drawing shear moment and then from moment theta and delta. We want to calculate again a delta maximum which happens at C due to the symmetry of the structure, and also theta A and theta at B. And most probably due to symmetry they are also identical to each other, and they are identical to each other. But we can have an intuition by looking the structure at the beginning. So let's see how that goes. If we draw shear diagram, it just goes by if there is a two simple support beam handling a concentrated load at the center, RA and RB just go by a half of that force. So RA is equal to RB, and that's a P over 2. Mhm. So if you are drawing the shear diagram, you are just coming up by the amount of P over 2. Then all the way to the center there is no nothing at from A to C, and all of a sudden a downward step with the uh, exact amount of concentrated load. So that's a negative P, that's a positive P over 2. So now we are at a negative P over 2. Then from C to B there is no nothing, so a constant line, and all of a sudden support at B, which brings us back to 0 by now uh, a half of a applied force. So from shear diagram, if you want to draw the moment diagram, it just gives you m. If we call that m over ei, if we just divide that by ei, it just gives us pl over 4 times ei. So how that goes, the area under shear, which is p over 2 times l over 2, because the total length is l, so that's pl over 4, the amount of maximum moment. And it just, there is no moment at the A, there is no moment at B, because they are not fixed, and the maximum is at happens at the center. So, and also the center, let's draw the theta from moment for now. So again, if we have m over ei, and if we want to know what y prime, so m over ei is y second, and y prime is just theta. So that's equal to theta. If this is m, this is a integration of that gives us to theta. And if you draw that, it just gives you a, if this is linear, this is a second degree order. And how that goes, the amount of theta goes by the area under moment. So if you do this calculation, it just gives you a half of area of this triangle. It just gives you a half of a L over 2 times PL over 4 EI. It gives you 4 times 4, which is 16 EI at the denominator, and theta or y prime is PL squared, because we have one L here and the other is L over 2, the length. And if you have a closer look at the trend of uh, moment here, as you can see, the numeric value of moment is increasing, so the slope of theta should increase. As you can see, there is a no slope, there is no nothing here, slope is 0, and it just start to uh, have a higher slope, because it's a kind of symmetrical, the other part is the same. So if you want to calculate area under theta is gives you the delta. So if we do know what our y prime or theta is, and this is a second order, this is a second degree. So the delta goes by a third degree uh, a curve. So let's see how that goes. It just goes by the a third degree spandrel. And if you want to calculate delta max, this is delta or y. This is y or delta, which is the integration of y or theta gives you delta. And y is equal to delta, isn't it? So if you want to calculate the maximum delta, it's just area under theta. So if this is second degree, that's, if you remember, this is a 2/3 of BH. So if you do the uh, calculation, it just gives you a delta max and just the area under, for example, any of them, because both of them are identical to each other. So that's a delta max is just goes by area of any of these two part. Forget about negative or positive, just the numeric value of that. Delta max or y is a 2/3 of b times h. So this is b, which is L over 2, and this is h, which is PL squared over 16 EI. And the length, definitely that's a half of the length of the beam, because that's L over 2. This is L over 2. The whole length goes by L, and it's divided a symmetrically based on both for two parts. And if you do so, it just gives you a delta max is PL cubed over 48 EI. Mhm. And that was just a drawing from a shear moment area under shear is moment area under load is shear area under shear is moment area under moment is a slope area under a slope is a moment. Likewise, you can integrate the uh, load by 4 times. You can also calculate the area under load, shear, moment, uh, uh, shear load, shear moment, and theta, and get the delta maximum. And that's, I think that's easier. You can also solve this problem with a moment area method, which is a simpler one. So solution to moment area method, it just gives you, if you want to calculate delta maximum, if you look at the geometry of the beam, you can easily see this is a tangential deviation of A from a reference line, like a horizontal line of C to A, isn't it? And that's exactly the amount of delta max at the center, isn't it? So if you know TAC is equal to delta max, and based on a second moment area theorem, it just says T delta max is equal to TA with respect to C, which is equal to area under moment times the distance to the first component. So that's a distance from centroid to A. And for a triangle, that's a 2/3 of L over 2. That's a distance. Uh-huh. And that's nothing but M over EI. That's M. That's area under M over EI, which we have here. Mhm. And that's what? That's M over EI from A to C times X bar. And that's our X bar from A. Centroid to A. That's a half of a area under a triangle, which is a triangle from A to C, that's here. That's a half of PL over 4EI, which is the height of the triangle, times L over 2, which is the length of the triangle, times 2/3 of L over 2, and it just gives you the same parametric value PL to the L cubed over 48 EI. And at the same time, if you want the theta from A to C, it's a area under M over EI from A to C, just based off the first uh, moment area theorem that gives you uh, the area of this triangle. It's a half of L times PL over 4 EI, which is PL squared over 16 EI. So one can easily say if we have a two simple support beam which happens to handle a concentrated load at its center, AB is a simple support beam at both ends and having a concentrated load of P applies at its center, it just gives us a delta maximum of PL cubed over 48 EI. We just calculated based on two methods of both drawing a shear moment, slope, and delta diagrams, and also from a second moment area theorem, which is a easier approach, and that just gives us a delta maximum of PL cubed over 48 EI at the center, and theta A and theta B are identical to each other, and they are just going by theta A is equal to theta B, and the numeric value of that is PL squared over 16 EI. We will solve more examples in next videos. Thank you.